today we will be studying about M-ary modulation. So we are dealing with passband modulation schemes. Then we have seen the binary passband modulation schemes like BASK, BPSK and BFSK. So today we will see M-ary modulation scheme. So what is M-ary modulation technique? So in binary data transmission, we send only one of the two possible signals during each bit interval TB. So in binary system, we will be either sending 0 or a 1. So corresponding to 0, either we will if we are using BASK, then we will use an amplitude. If BPSK, we will use a particular phase, and if it is BFSK, we will use a particular frequency. We have seen that. So during a bit interval TB, you will transmit only one bit or a signal corresponding to one bit. So either 0 or 1. But in M-ary data transmission, during each signaling interval capital T, we will send one of M possible signals, capital M possible signals. So during this M possible signals corresponds to M different, capital M different inputs. Okay. So this each of these M signals is called as a symbol. Actually, this one symbol represents n bits, a combination of n bits. So in almost all applications, capital M is equal to 2 raised to n. So that implies this signaling interval T equal to n into TB. The TB is the bit duration of a bit, capital T is the duration of a symbol, and we can see that, or please understand that, one symbol is a combination of n bits. അപ്പോൾ അതാണ് M-ary modulation. M-ary modulation എന്ന് വെച്ചാൽ നമുക്ക് ക്യാപിറ്റൽ M പോസിബിൾ സിഗ്നൽസ് ഉണ്ട്. Capital M possible signals. So during each signaling interval capital T, one of this capital M possible signals will be transmitted, and this signal will correspond to n bits, a combination of n bits, where n is always an integer, and this symbol duration is capital T, and this where capital T is number of bits into TB, where TB is the duration of a single bit. So each of these M signals are called a symbol, and then extending from the binary modulation schemes, these signals are generated by changing the amplitude, phase, frequency or combined forms of a carrier in M capital M discrete steps. So for binary, M was 2, and here it is, here we will have more than 2 symbols. Okay. ഇതിൻ്റെ അഡ്വാൻറ്റേജ് എന്ന് പറഞ്ഞാൽ നമ്മുടെ ഒരു സിഗ്നലിംഗ് ഇൻ്റർവെല്ലിൽ തന്നെ ഒരുപാട് ബിറ്റ്സ് അയക്കാൻ പറ്റും, n ബിറ്റ്സ് അയക്കാൻ പറ്റും, അതാണ് ഇതിൻ്റെ അഡ്വാൻറ്റേജ്. നേരത്തെ കേസിൽ ഒരു സിഗ്നലിംഗിൽ ഒരു ബിറ്റ്, ഏതർ 0 or 1 മാത്രമേ അയക്കാൻ പറ്റുള്ളൂ ഇൻ ബൈനറി സിസ്റ്റം. Now we have 4 different. Now we have four different schemes: MASK, that is M-ary amplitude shift key; MPSK, M-ary phase shift key, frequency shift keying; and MQAM. QAM is actually a combination of amplitude and phase. Okay. So both changes, amplitude as well as phase changes. Now we will start with M-ary phase shift keying. So in M-ary modulation, you will have M possible signals. So in M-ary phase shift keying there will be M phases, capital M phases, so which is represented as theta m equal to 2 pi by capital M into m minus 1. This starts from 0, then 2 pi by m, 2 pi by m into 2, 4 pi by m, like that, it goes like that. Then each phase represents a combination of n bits, small n bits, and small n is the number of bits and capital M is equal to 2 raised to n. So I can write the signal set as sum of t is equal to root of 2 es by t cos 2 pi fct plus 2 pi by m into m minus 1, where m is equal to 1 to m, capital M, and es is energy per symbol. So understand that es is energy per symbol, energy per bit was EB. So we can define two basis functions, phi 1 of t as root of 2 by capital T cos 2 pi fct, and phi 2 of t is root of 2 by t sin 2 pi fct. So we will be using, for M-ary phase shift keying, we will be using two basis functions, phi 1 of t and phi 2 of t, defined like this. Now this signal sum of t, I need to write this in terms of phi 1 of t and phi 2 of t. So sum of t is root of 2 es by t cos 2 pi fct plus 2 pi by capital M into m minus 1. So root of 2 es by capital T cos 2 pi fct cos 2 pi m minus 1 by m minus, so cos of a plus b, using that. Now I can write this as root es cos 2 pi by capital M m minus 1 phi 1 of t minus root es sin 2 pi by capital M m minus 1 phi 2 of t. So if I am converting this to the signal space form, or converting this to a vector of 2 dimension, so this sum of t is a point having the coordinates, a 2D point having coordinates root es cos 2 pi by m into m minus 1 root es sin 2 pi by capital M into m minus 1. So sum actually represents a single signal, and there are capital M's different signals like that. So each signal will be a 2D point in the vector space, or sorry, the signal space. So therefore small m varies from 1 to capital M, and sum is having two coordinates defined like this. Now we have to specify the value of this capital M to get the different PSK modulation schemes. So when m equal to 2, we will get S1 here and S2 here. So actually that is actually our BPSK. Capital M is equal to 2, then the points are root es cos pi 1. When capital M is 2, you need only a single basis function phi 1 of t, and we have only for BPSK, and the points are here 1 0 and minus 1 0, that we have already studied for BPSK. So m equal to 4, that is n equal to small n equal to 2, that is 2 bits combination. It is called QPSK, or quadrature phase shift keying. So we will have 4 points, S1, S2, S3 and S4. We will study QPSK in detail. Then 8 PSK, that is m equal to 8, the number of bits equal to 3. So you will have 8 different phases, one with each representing a particular signal. So m equal to 8 here, so you will have 8 signals. 1, 2. These 8 signals will be represented as 8 points in this 2D space defined by phi 1 of t and phi 2 of t. So 1, 2, 3, 4, 5, 6, 7, 8. These are the 8 points. And this is m equal to 16, called 16 PSK. So you can see that since only the phase is changing and amplitude remains same, all the points will be at the circumference of a circle. Now this dl represents the decision line. Now the Euclidean distance. So here we will be considering only the cases in which the symbols are bits are equiprobable. or messages are equiprobable. So for decoding we need to use only Euclidean distance. So Euclidean distance has an equation like this, and minimum Euclidean distance is 2 root ES sin pi by m. Now dmin is very important in determining error performance. The minimum distance is more means an error will be less. Now we will derive this for QPSK separately. Now quadrature phase shift game. So in quadrature phase shift game we use 4 states, that is n equal to 2 and capital M equal to 4. You have 4 signals, so we can transmit 2 bits for each signaling interval. We will be using a combination of 2 bits, so 0 0 0 1 1 0 and 1 1. So S0 of t is a cos omega 0 t plus 45 degree. We will be using 4 different symbols. So S0 of t is a cos omega 0 t plus 45 degree. S1 of t is a cos omega 0 t plus 135. We will be using 4 different phases: 45, 135, minus 135 and minus 45. So 4 symbols, and each symbol represents a combination of 2 bits. So this is the constellation diagram. S0, that is plus 45 degree, S1 plus 135, S2 minus 135 and S3 minus 45 degree. Okay. Now Si of t is, I can write it in a general form as a cos omega 0 t plus phi a, where phi a is 2i plus 1 into pi by 4. So if I am substituting 0, 1, 2 and 3 for this I will get this 4. So these are the 4 points: S0, S1, S2 and S3. This is the constellation diagram for QPSK. This is the phasor and this is the constellation diagram. Now this horizontal component is called as the I component, or this horizontal component is defined by our basis function phi 1 of t, that is cosine function, and vertical component is called as the quadrature component. This is represented by our, or this is defined by our phi 2 of t, that is the sine function. So phi 1 of t was root of 2 by t cos 2 pi of ct, and phi 2 of t was sine. So this represents, I represents cosine carrier and q represents the sinusoidal carrier, and I and q are shifted 90 degree in phase. So Si of t I can write it as ai cos omega 0 t, aq sin omega 0 t, where a is the amplitude in the amplitude of the in phase component, and aq is the amplitude of the quadrature component. So for I equal to 0, when I equal to 0, so this point S0, I equal to 0 is S0, so phi a is 45 degree and amplitude of both are positive, that is 1 1. S0 ആണ്, phi 0 വരാൻ നേരത്ത് ഈ പോയിന്റ് വരും, അതിൻ്റെ ആംപ്ലിറ്റ്യൂഡ്സ് 1 1, phase is 45 degree. So similarly when I equal to 1, phase is 135 degree, in phase component is negative, quadrature component is positive, that is this point S1. This in phase component is negative, quadrature component is positive. Then 2 and 3, this is in the third quadrant, both are negative, and this is in the fourth quadrant, both are positive. So this is 1 1 is mapped to 1 1, then minus 1 1 is mapped to binary data 0 1, minus 1 is mapped to 0 0, and 1 1 is mapped to 1 0. Now the block diagram for modulator. So each QPSK can be used, QPSK state can be used to represent 2 bits of data. So the incoming serial binary data must be multiplexed into group of 2 bits, which separately modulate I and Q components. So you can consider it like that. So incoming data is coming. Now we will group this into 2 bits. Then it is converted to parallel. That is, one bit goes to I channel and another bit goes to Q channel. Then you have a low pass anti-aliasing filter. Then this I channel, the bit that is gone through the I channel is multiplied by phi 1 of t, that is cos omega 0 t, and the bit that goes to Q channel is multiplied by sin omega 0 t, and it is added up to get the QPSK signal. So QPSK modulator thus takes the form shown in figure. A 90-degree inverter can be used to provide I and Q components of the local oscillator from a single oscillator. So this carriers are generated by a local oscillator. So you have two carriers or two basis functions, one cos and another sine. So because the average transmission between phases is 90 degree, the bandwidth of the QPSK is narrower. Now this is the pictorial representation. You have binary bits 0, 1, 1, 0. This is the input data. We will first group into 2. So 0, and the second one is here. So this is the I data. This 0 goes to the I channel and 1 goes to the Q channel. So next is 1, 1. So 1, 1. 1 goes to I channel, 1 goes to Q channel. Next is 0, 0. 0 goes to I channel, 0 goes to Q channel. Next is 0, 1. 0 goes to I channel, 1 goes to Q channel, like that. Now the 0, 1. 0, 1 will have a phase like this. Let's shift this stops here at the transition. Then you have 1, 1. 1, 1 will have a phase as like this. We have a total of 4 phases, 1 each for 0, 1, 1, 1, 0, 0 and 1, 0. We'll have a total of 4 different phases. So this is one symbol duration S1, and this one symbol duration represents 2 bits, 0 and 1. In BPSK it could represent only 1 bit. That is a difference. Here in one symbol duration I can send 2 bits in QPSK. In 8 PSK it will be 3, in 16 PSK it will be 4, like that. Okay. Now demodulator. So we will be using a coherent detector. So this QPSK can be considered as 2 BPSK signals in parallel or 2 BPSK modulated signals in parallel. So the demodulator uses 2 mixers with quadrature yellow components to recover I and Q signals. So 2 correlation receivers. So this is the correlation receiver for the I channel. So this is multiplier followed by integrator and sampler, that is the correlation receiver. So S of t is coming, it is multiplied with a cos omega 0 t, then integrated and then sampled at t equal to t. Similarly you have a detector for the second BPSK signal, that is the Q channel. Okay. So 2 BPSK receivers in parallel, and Vi is the received value for the I channel, and Vq is the received value for the Q channel. Then we will be using a 0 threshold. So each channel will be using 0 threshold. The threshold is 0, similar to BPSK. So this is the expression for a demodulator. Vi is a square cos omega 0 t plus phi a cos omega 0 t. So a cos omega 0 t plus phi a is actually our signal, and a cos omega 0 t is the symbol. So once the signal is received, a cos omega 0 t plus phi a is received, it is multiplied with a cos omega 0 t. So you will get it like this. So when you do, you will get a square by 2, a square capital T by 2 cos phi I, that is the one for VI, that is one for I channel, and for Q channel a square T by 2 sin phi I. So here we are multiplying with a sin omega 0 t. Now I and Q outputs of a QPSK demodulator. So for S0, both should be positive, it is in the first quadrant. For S1, second quadrant, this first term should be negative and second should be positive, so minus CC. In S2, that is in third quadrant, both are negative, and S3, first is positive, second is negative, so 1 0. So we can assign bits to these signals in any different way, but what we do is we mostly use a gray code assignment. So gray code means that these two adjacent symbols, they differ only by a single bit. So this is because when an error occurs in the detection of a symbol, it is most likely that only one of the bits will be in error rather than both the bits. So that is why this gray code is important. It is because error is most likely to result in a shift from correct phase state to the immediately adjacent phase rather than diametrically opposite phase. ഇപ്പോൾ ഫസ്റ്റ് S0 അയച്ചാൽ S0 എന്ന് വെച്ചാൽ 2 ബിറ്റിൻ്റെ കോമ്പിനേഷനാണ്. അപ്പോൾ ഈ S0 നോയ്സ് കടന്ന് റിസീവ് ചെയ്യാൻ നേരത്ത് അത് ഏറ്റവും അധികം സാധ്യത S1-ലേക്കോ S3-ലേക്കോ പോകാനാണ്. അങ്ങനെ വരുമ്പോൾ S0യും S1 അല്ലെങ്കിൽ S0യും S3യും തമ്മിൽ ഒരു ബിറ്റിൻ്റെ ചേഞ്ച് മാത്രമേ ഉള്ളെങ്കിൽ ഇറ്റ് ഈസ് ഗുഡ് ഫോർ us ബിക്കോസ് ഒരു ബിറ്റ് മാത്രമേ എററിൽ പോവുള്ളൂ. ഓക്കെ, so that is why gray coding is done. Now we'll calculate the probability of error of QPSK. So assume that the error rates for all SI are equal by symmetry. Assume that S1 is received. So S of t, so the received signal is S1 of t plus n of t. S1 is having a phase of 135. So a cos omega 0 t plus 135 degree plus n of t. Now VI of t. So this is the output of the correlator. So it is, so you can do this as an exercise. So when this is passed through the integrator and multiplied with a cos omega 0 t and do the integration from 0 to t, what we will get is minus a square t by 2 root 2 plus n0 of t. n0 of t is the output of n of t passed through the correlator, that is n of t multiplied with the carrier, then integrated from 0 to t and sampled at t equal to capital T. So that is n0 of t. So VI of t is minus a square t by 2 root 2 plus n0 of t. So that is minus ES by root 2. Minus a square by 2 is the symbol energy. Sorry, a square by 2 is the symbol energy. So it is a square t by 2 is the symbol energy. So it is minus ES by root 2 plus n0 of t. Similarly, VQ of t, the received one, is a square t by 2 root 2 plus n0 of t. So to obtain this, you have to multiply this signal with a sin omega 0 t, take the integral from 0 to capital T, then you will get this a square capital T by 2 root 2 plus n0 of t. So these two are the received vectors for I channel and Q channel respectively. The ES equal to S square T by 2 is the simple answer. Now N0 of T is A into N of T into A cos omega 0 T, and integrating from 0 to infinity. So this is a Gaussian random variable. You can see because N of T is a Gaussian random variable. This is also a Gaussian random variable. So its mean will be 0, because when you take expectation can be taken inside E of N of T is 0. And we find variance of N0 of T as follows. So this is straightforward, we have already done. Variance is ES into N0 by 2. Now the detection threshold for both the detectors is 0. So we will consider the probability of symbol at the I correlator first, the I channel. So S1 of T in the I channel. So we are assuming that S1 of T was transmitted. For the I channel, S1 of T is negative -1, and for Q channel it is +1. So remember that. So the probability of symbol error at I channel is, normally this I channel should be less than 0. 0 is threshold. So error means that probability that VA is greater than 0. So probability that VA is greater than 0 implies probability that VI, we get it from here, minus ES by root 2 plus N0 of capital T. So this should be greater than 0. So that implies N0 of capital T greater than ES by root 2. So N0 of T is actually Gaussian distributed with mean 0 and variance sigma square. So this is the Gaussian expression is 1 by root of 2 pi sigma square e raised to minus N0 square by 2 sigma square. So that should be greater than ES by root 2. So integrate it from ES by root 2 to infinity. So you can write this as, so here we will use error function here. In the last, for BPSK we used Q function. So both anything can be used. So I can write this as ES by 2 sigma to infinity 1 by root pi. This is actually error function. So half into error function of ES by 2 sigma, or we are substituting for sigma. Sigma is ES into N0 by 2. So this is equal to half into error function root of ES by 2N0. So that is the probability of symbol error at I correlation. So by symmetry we also obtain the same expression for the probability of symbol error at Q correlator. By symmetry, at Q channel name same then every half into error function root of ES by 2N0. So this is the probability of error for both the channels I and Q. So the probability of correct decision will be 1 minus half into error function of root of ES by 2N0 for I channel, and for Q channel also it will be 1 minus half into error function root of ES by 2N0. So there are two bits in a symbol. So symbol will be in error if either one of these two bits are in error. So this is the probability of error for bit in I channel, and this is the probability of error for bit in Q channel. So the symbol will be correctly decoded only if both are correct. So probability of correct decision is 1 minus PEL into 1 minus PEQ. ഇത് രണ്ടും കറക്റ്റ് ആവണം. ഇത് I ചാനൽ കറക്റ്റ് ആവുള്ള പ്രോബിലിറ്റി, ഇത് Q ചാനലിൽ നിന്ന് കറക്റ്റ് ആവുള്ള പ്രോബിലിറ്റി. ഇത് രണ്ടും കറക്റ്റ് ആയെന്ന് വെച്ചാൽ രണ്ടുകൂടെ മൾട്ടിപ്ലൈ, രണ്ടും കറക്റ്റ് ആയാൽ മാത്രമേ സിമ്പൽ കറക്റ്റ് ആവുള്ളൂ. So the overall probability error for a symbol is 1 minus probability that both I and Q are correct. So that is the probability of error. So this PEI and PEQ are equal. So I can write, so let it be PE. So I can write it as 1 minus PE the whole square and when you expand it you'll get, so there is a 1 here, so that is missed, 1 and 1 cancel out, minus or minus is plus 2 PEI or Q, both are same, plus PEI the whole square. So we assume that PE is much smaller, so PEI the whole square can be neglected. So this is approximately equal to 2 PEI, that is I channel, or 2 PE, both are same, I ന്റെയും probability of error same ആണ് ഇവിടെ നമ്മൾ കണ്ടത്. So that is error function root of ES by 2 N naught. That is the overall probability of error for a symbol. So since each symbol contains 2 bits, the bit error rate for QPSK will be 1/2 of the symbol error rate. So the bit error rate will be half into error function root of ES by 2 N naught. Now because the symbol period T is twice the bit period, E is equal to 2 EB or ES is equal to 2 EB. Symbol period is twice the bit period, where EB is the bit energy. So if you substitute it, you will get half into error function of EB by N naught, error function root of EB by N naught. So that is similar to the probability of error for BPSK. So BPSK probability of error നമ്മൾ Q ഫംഗ്ഷനിലാണ് കണ്ടുപിടിച്ചത്. അത് എറർ ഫംഗ്ഷൻ വെച്ചാണ് കണ്ടുപിടിക്കുന്നതെങ്കിൽ യു വിൽ ഗെറ്റ് ഇറ്റ് ആസ് ഹാഫ് ഇൻറ്റു എറർ ഫംഗ്ഷൻ റൂട്ട് ഓഫ് EB by N naught. അതേ പ്രോബിലിറ്റി ഓഫ് എറർ തന്നെയാണ് QPSK ഇവിടെ കിട്ടുന്നത്. ഇഫ് യു സബ്സ്റ്റിറ്റ്യൂട്ട് ES equal to 2 EB. So the most important thing is QPSK is really efficient. QPSK is twice as bandwidth efficient as BPSK, but it has the same probability of error. BPSKയുടെ അതേ പ്രോബിലിറ്റി ഓഫ് എറർ ആണ്, തെറ്റാനുള്ള സാധ്യത BPSKയും QPSKയും സെയിം ആണ്. പക്ഷേ BPSK ഒരു സിമ്പലിൽ ഒറ്റ ബിറ്റ് ആയിരിക്കുള്ളൂ, ഇവിടെ 2 ബിറ്റ് ആയിരിക്കും. So this is bandwidth efficient. So there is an example. So this is not that important. If you are interested, you can try out this. Here where they are finding probability error for BPSK as well as QPSK. So you got it as the same. Bit error rate for QPSK and BPSK are identical. There is another exercise also. So for us, they usually ask theory only or derivation. Problems are not always asked from this topic. So this is the error performance of MPSK. This for BPSK and QPSK the error is almost same. Then for 8PSK error is more. There is 4 dB difference. Then 5 dB difference between 8 and 16. And 32 and 64, 6 dB difference is there. Now MQAM. So in MPSK, in phase and quadrature components are interlaid in such a way that envelope is constant, or we are get a circular constellation. So if we relax this constraint, if we change the amplitudes also, we will get M-ary QAM. This is the example of 16 QAM. So this is 16 PSK. Only phase is changed for the symbol, so all will be in the circumference of a circle. So here in QAM both amplitude and phase changes. So this is a square constellation for 16 QAM. So this is the equation. Root of 2 E0 by T AI cos 2 pi FCT plus root of 2 E0 by T BI sin 2 pi FCT. So root of phi 1 of t is root of 2 by t cos 2 pi FCT, and phi 2 of t is root of 2 by t sin 2 pi FCT. So you can see that the amplitude is also changed here. Not only phase, the amplitude is also changed. Now the sequence phase representation is root of E0 AI, root of E0 BI. That is QAM. Both amplitude and phase changes. This is a combination of phase modulation and amplitude modulation. This is the This is the constellation diagram for 16 QAM. So you can see that each symbol represents 4 bits. So here we are using a gray code mapping. As you can see, two adjacent symbols changes only in a single bit. So that is for reducing the probability of error. So this is when m equal to 64. This constellation m equal to 32. So m equal to 16, m equal to 4. M equal to 4 is actually QAM. Sorry, 4 QAM and QPSK are same. QPSK, 8 QAM. This is also possible. So for these symbols, both amplitudes as well as phase is changing. And this is 8 PSK. This is in a circle. This is 16 BSK, 16 QAM. So these two different. This is star 16 QAM and this square 16 QAM. So this 64 QAM, this QAM is used widely in many wireless and cellular technology applications. Then 64 QAM to 6 QAM is used in digital cable television, cable modem, like that. This QAM has a lot of applications. So this is a similar probability for QAM. This derivation is not required. Now MFSK. So in MFSK, there will be M different frequencies. Each will select SM of t in such a way that each represents a combination of small n bits. So there will be a total of capital M symbols. Each symbol will be having a frequency. Each symbol will be having different frequencies. We will choose capital M different frequencies. So usually it is represented like this: Sm of t equal to root of 2 es by t cos 2 pi fc plus m minus 1 into delta f into t, where delta f is some fm minus 1, or fm equal to fc plus m delta f. Now this frequency should be selected in such a way that all these signals are all the basis functions are orthogonal. So here you have m basis functions. ഇതാണ് ഒരു M-ary PSK അല്ലെങ്കിൽ M-ary QAM MFSK തമ്മിലുള്ള വ്യത്യാസം. ഇവിടെ നമുക്ക് ക്യാപിറ്റൽ M ബേസിസ് ഫങ്ഷൻസ് ഉണ്ട്, അത്രയും ബേസ് ഫങ്ഷൻസ്. സോ വി വിൽ ബി ഡീലിംഗ് വിത്ത് എ ക്യാപിറ്റൽ M ഡയമെൻഷണൽ സ്പേസ്. നേരത്തെ പോലെ രണ്ട് ബേസ് ഫങ്ഷനായി 2Dയിൽ നമുക്ക് ഇതിനെ കാണാൻ പറ്റില്ല. So this has capital M different basis functions. So each basis function will be having a different frequency. FC plus delta f, FC plus 2 delta f, etc. FC plus M delta f. So there will be a total of capital M different frequencies. All are orthogonal to each other. So ഈ ഓരോ ഇതും നമ്മൾ M ഡയമെൻഷണൽ സ്പേസിലാണ് വ്യൂ ചെയ്യേണ്ടത്, 2Dയിൽ പറ്റില്ല. So this each base function can be represented like this: S0 root of ES00, S1 0 root ES00, Sm minus 1 0 0 0 0 etc. root ES. So this is the basis function. Phi m is root of 2 by t cos 2 pi fc plus m delta f into t. So in the constellation diagram requires M dimensional space, and each point will be in the axis S0 to Sm minus 1, each of the M axis. All our coordinates are 0. So this is the error performance of MFSK. Now summarizing. For BPSK, you have 1 bit per symbol. So symbol rate is 1 into bit rate. UPSK you have 2 bits per symbol, so it is half into bit rate, symbol that is half into bit rate. 8 PSK symbol that is 1/3 of bit rate. Then 16 QAM symbol that is 1/4 of bit rate. 32 QAM is 1/5 of bit rate, and 64 QAM is 1/6 of bit rate.